So I'm going to go through kind of a high-level view, more, I guess, actually more into the details than I did yesterday about what the actual data that the LSST is going to produce. What is it going to look like when you go to the science platform, look at the databases, what are the measurements going to look like? And how do you, I think the most important thing is how do you combine the various properties that we measure in order to extract this particular science that you want to do. I've tried to keep this at a sort of manageable level of slides so that you can ask me questions about this as we go along. It's kind of, these are all kind of dense topics because a lot of it kind of requires adjusting one's view of how you would do this measurement to the way that we've planned out the system as a whole. So the key, like the most important thing here actually is that everything I'm describing is all written down in what we call the data products definition document. So if you go to that link, ls.st/dpdd, that is the high-level document describing exactly what goes in the database, what are all the fields that we're measuring, how do those different tables relate to each other. This doesn't necessarily go into the details of how does one do a specific measurement. We don't say, it's not telling you how to do PSF photometry or how to measure centroids of sources. It's saying that we will definitely measure PSF photometry, we'll definitely measure aperture photometry in these particular contexts so we can then sort of fill in the details on exactly what those measurements are at a later time. But everything, if I say anything that's confusing, you can always go back to the DPTD and it should really have the definitive statement on what we're doing. And if it seems like it's confusing or if it seems like it's saying something that doesn't make any sense, please let me know. I am always interested in fixing things in this document that are mistaken or that are just not usable by the science community. So just to show you a little bit of what this looks like, this is an example table for the DIA object, and I'll describe a little bit more what that means in a minute. But we list the name, we list what type of, sort of what data type it is, the units, and a little bit of the description for each of those fields, and then that goes for all the different tables that we have in the database. So there's a lot of moving parts, and so one thing I want to clarify is that we have two different categories for the data, and these are tied to the time scale on which they are produced and released. So we think of the prompt data products as the measurements that are done every 37 seconds. As soon as the image comes in from the telescope, we measure all of the prompt data products on that data in the middle of the night. Those all get distributed in alerts, they get saved to databases, etc. The data release products are the separate cadence that happens every year. I mentioned some of this yesterday, but that's reprocessing all of the data. Both of these have lots of time domain information. So a common misconception is that people think that, well, because I want to look at time series information, it's all going to be in the alerts, it's always going to be in the data that's coming every night. That's not quite how it works. We've designed it so that the alerts are primarily focused to give you the information that you need to follow up tomorrow night, later tonight, to bring your larger telescope to get spectra of an interesting object. If you're just interested in sort of longer time series information, you're not worried about slewing your large telescope to that source right immediately, the data release on an annual cadence also has that time domain information, and in many cases it has better time domain information because we are able to look at the entire history of the survey all at once. We don't have this 60-second deadline to get out the information, so it will give you higher quality measurements in most all cases. So you can kind of see that these are somewhat orthogonal concepts of the time domain versus quasi-static science cases and the nightly versus annual processing. We don't do any nightly processing that would be useful to the static sky. We just measure enough of the sources in order to do astrometry and photometric calibration, but then we immediately go into difference imaging. So most of the static sky cases, if you're interested in coads, if you're interested in measurements of galaxies, that's all going to be in the annual data release. release, but then so is the image differencing. We will re-difference all of the images taken in the history of the survey every year, so we'll always have new detections of difference image sources. I showed this yesterday, but just to remind everyone that we're really talking about the contents of the alert packets, and these also go into the prompt products database. There's a few acronyms that I want to clarify because they get used quite heavily. So if you see DIA, that gets prefixed before a lot of tables. That stands for difference image analysis. That usually means that the data or that the measurements are made on a difference image. They're not made on a static image that's just a picture of the sky. So we talk about a DIA source. That's a source that's measured on a particular difference image. We use source to mean an individual appearance and object to mean the summary of those sources that appear at the same point in the sky. This is always a problem because every survey kind of picks which way they want to do this. Gaia uses source and object in the exact opposite meaning, so I'm sorry for that. So the DA source will give you all the information that's contained in one image, and the DA object is really a summary of my favorite variable star, where we try and take all the information and put it together in some way that's meaningful. You also see that we're talking that we measure solar system objects. Those, if we know about the object already, we propagate all the orbits of all the objects we know into the field of view, and so we can identify them immediately if they've already been known to the Minor Planet Center. If not, those difference image sources will get passed to a separate code which does identification of moving objects during the day. So you won't have immediate access to those during the night if there are new discoveries, but you'll get them by the start of the next observing night. So just to make this a little more concrete, some examples of the DA source fields. So this is a list that's just fully pulled from the data products definition document. We measure PSF flux, we measure aperture flux. We do trailed measurements. If the source is a solar system object, it's likely going to be moving, and if it's moving fast enough, then it will produce a little streak in the image. So we have code that will measure those trails. If it's something like a star that's moving very slowly, but it exists on our template image, you might see that it moved half of a PSF width, and so you'll get a dipole in the difference image. You'll get a positive lobe and a negative lobe. That's just because the source moved a little bit. So in addition to doing pure PSF and aperture photometry, we'll also model that dipole structure, so you can say, oh, this is a source that it just moved a little bit. That's why it appeared in the difference image. So we'll measure how far did it move and what's the flux in those two relative lobes. And we also do a few other adaptive moments, which is mostly to detect extended sources that appear in difference imaging, so comets basically. DA object is that summary of the DA sources. So it's almost always of the form. It's a mean of all the PSF fluxes seen in the DA sources associated with that object. We go back 12 months, so we're always giving you a summary of the past 12 months history of whatever that object was at that position on the sky. So we'll give you a mean of the PSF flux. We'll give you also a standard deviation and an uncertainty on that, so you can tell, does this have fluctuations in the individual measurements above and beyond what you would expect from just Poisson noise? This is a nice way to get at really variable objects in a crude way. Does it just have more variability than we would expect from a constant source? We measure a variety of light curve features. So these are not described in great detail. We expect to define them better when we get closer to the start of operations. We'll take whatever the sort of latest and greatest method is for identifying variable sources, we'll want to incorporate those into our light curve features. So just as an example, the basic Lomskargel Light curve peaks will just do the periodogram, measure what the frequencies and amplitudes are of the first 2 or 3 peaks or so, and return those. This is mostly just to give you a way to search the database of DA objects, find candidates that are interesting enough to go look at the full light curves, and then go download just that subset of light curves from the database. So you don't have to search all of the light curves of the entire survey to find your favorite variable star. We do this both for periodic features and for non-periodic features. So we hope to incorporate to support a wide variety of science cases by making these kind of broadly useful features. This is just a flow chart of what the operations look like in alert production. So we start at the top, we get a new image. The template that we're going to difference against it comes from the data release production that happened most recently. So that will give us the latest and greatest difference image built up from a coad of many different images in the past years. We do that difference imaging. That gives us the DAA sources. We combine that with the history of previous DAA sources to understand, is this something new? Have we seen anything in this position on the sky before? If so, we call that a new DAA object, and we'll measure some parameters about it. If we have seen something else in the same position on the sky previously, we will associate those two together, and so now we'll rebuild that DAA object so that it has the new latest and greatest history and the latest and greatest set of properties of the variability statistics. So you'll be able to know from the alert, is this a new thing likely to be a transient, or is this something that we've seen every single time we've come to this position on the sky? Those go to, the output of that goes to both the alerts and it gets stored in the database. So we have a database that stores the DAA sources and the DAA object records. So you don't have to get all of the time-sensitive information purely from the alerts. We will also store those in a way that you can just query offline whenever you want. It doesn't have to be, you don't have to be sitting there waiting in the alert stream just to get your favorite object. You can if you want. We're totally also interested in supporting that. So the alerts go both to community brokers. These are a set of, we think about half a dozen organizations who've stepped up to process the full alert stream, and also goes to what we call a simple filtering service and alerts database. And I'll talk about those both in a minute. What goes into the alert itself? So we want these packets of alerts to be fully self-contained, so that you have all the information that you need in order to make decisions about, do I follow this up? Is this an interesting thing that I need to think about right now, tonight? So we include the DAA source record. That's just the measurements on the image itself. We include the DAA object, which has that history, and all of the individual previous measurements of that DAA object. So if we've seen this 10 times in the past 12 months, you get those measurements from each of those past 10 times. So you can both use the variability statistics that we've computed, or you can use that data to compute your own metrics to decide, is this an interesting source to you? So you'll have that history available. If we haven't detected this source before, we'll also tell you what the upper limits were on previous images taken at that point in the sky. This is particularly useful to groups like the supernova community. They want to know that something appeared here and that it was also, like, there was nothing there last night or an hour ago or a week ago, because then it tells them very tells them very well how quickly this object, the light curve, rose. So that those are all upper limits. They're not meant to be extremely high quality. They're just mostly meant to enable classification. Is this interesting or is this not? We match to the objects from the last data release. So if you A lot of times, again, just using supernovae as an example, you want to know, is this sitting in the middle of a giant red elliptical galaxy, or is this in the middle of nowhere, or is this sitting in some spiral arm of a blue galaxy? So we'll do that cross-match so you know exactly what object in the data release you want to think about that association with. We return several of these, so we don't want to make statements like we know that this object is definitely associated physically with some object in the data release. We will give you a few of the nearest stars nearby and a few of the nearest galaxies nearby, and then it's kind of the burden's on the user to decide what makes the most sense as a physical association between these objects. So we want to kind of be agnostic to, are these just co-located on the sky, or are they actually physically related? And we also, we provide the cutout images, so we'll give you at least 30 by 30 pixels of the science image, and the difference image and the template image should give you enough to sort of say, is this a satellite trail or something weird, or does it actually look like a good point source? So those are just kind of listing the different outputs for data in the nightly processing. So at the top, you have the prompt products database. That's the database that will be sort of most useful if you just sort of want to query for the past month or so of objects that might have some variability properties that you're interested in. You can go do all sorts of SQL queries on that. It's available whenever you like. You can use this as a kind of an alternative to sitting on the alert stream and having to have something running constantly. The alert brokers I mentioned before, that's really focused on adding more information. So a lot of alert brokers are interested in cross-matching the alerts to other catalogs. So they have a set of known X-ray variable sources, and they can add that information to the alert and give that to users who are particularly interested in flares of X-ray binaries. They'll get that information in the alerts downstream of that particular broker. We expect the alert brokers we expect some of them to be sort of general and just kind of cover a wide variety of cases, but we also expect some alert brokers to be very focused on delivering their specific science cases. And again, we have not chosen alert brokers. We expect this to be a proposal process that happens starting next year. The outputs from all the alert brokers, that is the responsibility of the brokers to distribute to the users. We do not bring those back to the LSST databases. You need to go through their channels to get that data from them. If the alert brokers do not meet the science needs that you have, or if you're interested in sort of much simpler requirements for interesting alerts, we provide a simple filtering service. This is available to all users with data access rights. And what this does is it lets you filter just on the properties of the alert itself. So it does not enable cross-matching. We will not have, like, as an example, that set of that X-ray catalog to cross-match against. But if you know, I just want to know everything brighter than, or changing by more than 3 magnitudes in a difference image, just send me those alerts. You'll be able to sign up to receive those alerts from the simple filtering service. There's a limit to the number of these that you can receive. It's mostly just a bandwidth limit, but we expect this to be, it's sufficient given the number of images we're going to be taking. And just lastly, in terms of where this data goes, there's also an alert database, which is mostly just a repository of the alerts themselves. It's not necessarily designed to be quite as searchable in a fully featured way as the prompt products database, but if you saw an alert go by and then you accidentally deleted it, but you've saved the ID number of that alert for some reason, you can go access it again. You can make sure that the data is still, like, you haven't accidentally modified the alert or anything like that. So it's kind of to enable repeatability. Okay, so as I was saying at the beginning, the annual releases also have this time domain information. So for each object, and we define an object as both anything that appears in a coad of all the data, or anything that appears in difference imaging done during data release production. So we'll go back, build a new set of templates, do differencing of all the images again in the data release production. That will produce a new set of DAA sources, but we'll combine those in a way with the COAD information, so we have a set of objects. These should be this, we think of this as the union of both all the static and all the varying sources that really, we want to do the full suite of measurements, both COAD measurements and time variable measurements on that set of objects for the entire history of the survey. So this ends up in this table that we call forced source. So I have an object. I will then go measure force photometry at the position of that object throughout every image that this appeared in, or that overlapped this position of the object. So this gives you another way, as I was saying at the beginning, that if I have a variable star, every year we're going to get a new data release that's going to have a new set of measurements of the entire history of that object. So you do not have to worry about taking all of the alerts from that year or from the history of the observatory to get that entire light curve. So just to illustrate, it's we have one force source for each object, for each visit that overlaps it, and you should be able to just easily pull out, give me all the force source measurements for my favorite object. So the typical workflow we expect is that the object will have the same sort of variability characteristics, characterization numbers that we provided for in the alert production. So we'll have those Lomscargle peaks, et cetera, RMS flux variations, et cetera. You'll be able to say, give me all the objects that have RMS flux variations greater than whatever your limit is that you're interested in, and then for each of those objects, go give me the entire light curves from them, from the force source database for all those visits. I think that was a little dense, so I don't want to go too much further than that. There's a lot of routes to the information in the LSST databases, and there's a lot of different databases to kind of keep in one's mind. So we're always happy to think about your particular case, how to extract that information from the data products that we're building. And we're always also happy to figure out new ways that we can enable other science cases that we might not have thought about that weren't quite accommodated by the model that I've described today. Again, if you have questions about this, I'd love to answer those questions, but also you can always go to the data products definition document. If that does not answer your questions about data model, I'm also happy to hear about that, so to find ways we can improve it. So happy to take questions at this point.
Thanks, Colin. Any question?
Do you have any statistics of how many alerts do you expect to receive? Because at some point, if you know which one is more interesting than the other, maybe because you are not going to have the time to do the follow-up or to study more specific objects. So how can you select which is the most important or interesting alerts that you will receive?
How can the user select that?
Yeah.
Okay. In large part, I think that's up to the user to decide what's the best way to do that. So everything I described in the alert packet or in the products the prompt products
databases?
In
the other contexts you mentioned, but it will be a huge amount of alerts, right? I don't know what the number, if you know the number of alerts that you will expect to receive each night, for example.
I think it's on the order of 10,000, but that's a very hard to characterize number. Mm-hmm. So I think you have to decide what those cuts are that you make on those fields, mm-hmm. such that you're not receiving 10,000 alerts. You have to cut it whatever it takes to get it down to a manageable number. It's a very science case by science case decision. I don't have a broad scheme for that.
Yeah, sure. Okay.
do we need really the microphone? Okay.
That's good.
Okay, Colin. Thank you very much. Very clear. Okay, sorry. Perfect. So I have a curiosity and a question. The curiosity is that I don't know whether I missed, but you didn't talk at all about astrometry. This means that somehow you are planning to put together the catalog only because your reference image is going to be your master reference image and everything is scaled, moved into the same geometrical solution, or whether you plan to have absolute astrometric solutions for the objects in all the images that you are going to collect.
Astrometry is a complicated story, as I'm sure everyone's aware. So in difference imaging, that is purely an operation which maps those two images to each other. So we will take the template, which is a coad, so it's on an idealized coordinate system. We will warp it to the science image. So we will try and match those pixel for pixel with some mapping function. And computing that mapping function is a complicated operation, but it's doable. That gives us, that's how we get astrometry from difference imaging. So we'll then have a
relative astrometry. Is just the shift of the sources within that image. That pointing, let me say.
So relative and absolute astrometry get a little messy in the era of LSST, right? Because we will have Gaia stars. Okay, so I should just say the plan for data release production is that we will start with the Gaia reference frame, so we'll have those stars across the entire survey, and then because we go 4 magnitudes deeper, we will be able to compute higher order corrections on top of that Gaia frame. So we'll have a deep astrometric reference catalog that is rigidly tied to Gaia. At that point, whether you call that relative or absolute astrometry, I'm not actually sure. It's complicated. So.
Okay. In any case, the information is implicit because it talks about solar system.
But this is one of the issues in the sense that all the times that we are going to receive a catalog, we are going to have, in any case, the astrometry associated.
Yes, definitely.
Okay, that's the main point. The second thing that I was, once again, I hope that I didn't miss. I remember that in one of the last meetings, I think that Bob mentioned the possibility to use some training data sets that you have already processed with the LSST pipeline. I am talking about images that have been collected with the hypersuprime cam and with the DECAM.
Yes.
I was wondering whether we might have access to this kind of information to see what kind of analysis, what kind of results you have already obtained with those images.
Yeah, so the hypersuprime cam data is available publicly, but it's not quite, it has a different data model because it's done by hypersuprime cam survey people. It's using our pipelines, but the outputs don't necessarily correspond in the exact same way as I've described here. So they're much more focused on measurements of coads, measurements on coads themselves, and I don't believe they have the same difference imaging available in that data set. So I guess it depends sort of what your goals are specifically, whether that's sufficient or whether you really need something that looks more like an LSST cadence.
No, is it just to see what kind of quality we can extract from those images? So if they are available to the community?
Yeah, so I think then it is fine to look at the HSC data with a little bit of a grain of salt that like we still have 4 years of improvements of all of these products to make it sort of if it diverges a little bit from what I've said today, it's because we still have development to do, and so it will get better.
So actually I wanted to bring back the comment about how you will select the alerts, not so much as a question to Colin, but rather as a question to you all, because I think this requires a lot of thoughts and a lot of organizing and planning. And there are not that many. Colin mentioned there's a number of teams that are responding to the call, but all in all, there are not that many. There's maybe like 5 competitive teams that are setting up brokers at the top that I know of, and they're trying to distribute the alerts to all of the world. So I think the Europeans need to think about it thoroughly. Stephen Barnes is leading the what's it called?
LSST is the Chilean one?
LSST is the Chilean one. I don't remember.
You're talking about the UK?
Yeah.
I forget.
Yeah, with some Gaelic name or something. What's it?
Lassa?
LSST, yeah.
Something.
Right.
Something like that.
But so I think it's time for the rest of Europe to pressure them into understanding whether they're going to distribute the alerts to everybody, whether they're going to be specialized, they're going to distribute a subset of the alerts, what they're going to do with data that is proprietary, that they're going to join with the LSST data, and with users that may not have access to those other data sets. Yeah.
I completely agree. I guess we want to make sure that it's not, we don't expect every single organization to have to develop an alert broker. We're trying to make it so that's not necessary. But again, if the ones that are proposed don't meet your needs, then that's a serious problem. And like, it's hard to address that the later you wait. So I agree, it requires discussion with those teams sooner rather than later.
The reason why I mentioned it was because of Gabriella's question. And so you select the characteristics of your transients. So the working idea is that you know the characteristics of your transients. You know if your transients is red or blue, fast rising, fast declining, slow declining, whatever. And you select in that parameter space. And most of the brokers are planning on providing user-selected filters. But not all of them are going to enable you to write your user-selected filter on the fly right when you want. And they need to start training their data to understand if they can use a user-selected filter. So it's really time to contact the brokers now so they can set up to provide what the community needs.
Thanks.